Thanks for the introduction, and thanks everyone for being here. It's an honor to talk to you today. I realize that being unable to walk is going to be a bit like a speech impediment for me, but I'll try my best. I'm going to tell you about our work at Google Research, Google Brain back then, now part of Google DeepMind, on automatically discovering machine learning algorithms from simple primitives. First, I'll start with a project from 3 years ago called AutoMLZero, where we asked of AutoML too much on purpose. The idea there was to see if we, the experimenters, the researchers, tie our hands behind our backs and give the system as little information as possible about machine learning, but instead throw data at it and see whether it could come up with solutions, whether it could discover learning. And it did, in a toy setting. Since then, what we've done is make compromises on that amount of knowledge that we give it, meaning we give it some instead of none, or we give it more instead of little. And instead, and thanks to that, we get out of the toy setting and into realistic problems and even state-of-the-art. So let's start at the beginning. This is work done with Chen Liang, David So, and Kwok Le. And we evolved code at the code level. By minimizing the knowledge that we give it, I mean that we're going to use only simple operations like additions and multiplications, and we're going to let it start from a blank slate. And this way, in this context, is where learning emerges. So why do that? First, why do AutoML? And here, of course, I'm preaching to the choir. But as you know, machine learning requires rare expertise. There's not enough experts to go around, so we'd like to automate it. It can also be boring sometimes, so we'd like to, for example, have good automated HPO methods. And maybe we can even find better models, and this was the goal of architecture search, is still. Architecture search combined large hand-designed components like dilated convolutions and Pachenon layers and so on, to try to discover new models. Okay. AutoMLZero was different in the sense that we only used basic mathematical operations. In particular, gradients and backpropagation were not in there. If it were to discover a method that needs gradients, it has to discover the gradients too. Few restrictions on form, which means that we evolve at the code level, line by line, as it were. And we search for the whole of the algorithm. So not, for example, we don't assume that there is a backward pass, that we have the gradients. That's part of the search. Data augmentation has to be part of the search. The optimizer has to be part of the search. So why do that? Well, the hope is that by giving it little prior knowledge, we reduce the bias that we put into the system. If you start from prefabricated rooms, you will probably get something that looks like a prefabricated house. If you wanted to get something else, something more unexpected, like the Taj Mahal, and you don't have the Taj Mahal prefabricated parts, then you better start with smaller components, like stone and cement and so on. And if you have enough time, something might happen. Credit where credit's due. Of course, discovering code automatically had been a thing for a while. Most of the recent work had focused on tasks like string manipulation and sorting and so on. The difference is that we considered ML the task. Of course, on having ML the task, there is, as you well know, a lot of prior work too. Here, it wasn't at the code level. It was typically, as I had mentioned before, with the large components. Search for the architecture, the data augmentation. Search for the blank would typically give you a paper a few years ago. What we wanted to do is all of it at the same time and from scratch. So let me tell you how. We had a space of simple programs that we wanted to search. These programs were made up of functions that all read and write from a shared memory. This memory looks like this. The numbers are addresses in it. And there are 3 address spaces for scalars, vectors, and matrices. And this could be the code of a function. And it does what you think it does. Take a number 2 and put in scalar address 3. Take this vector, put it in there, read them, multiply them, and write the output there. That's the level at which we are evolving. And I said we were going to search for algorithms, and for this purpose, we define them as a triplet of functions: set up, predict, and learn. And these also do what you think they do. So once an algorithm is proposed by the evolutionary system, which I haven't told you how, I will tell you soon, we have to know how good it is. And to do that, we just throw data at it. Namely, we first execute the code in the setup function, and then we enter a training loop where we write the features to a certain location in the memory. It's always the same location so that it can evolve to use that memory location, and then execute the predict function. No matter what is in the predict function, we execute it, even if it's nonsense, if it wants to divide by 0, whatever. Then we write the label, and we call the learn function. Okay, and then we enter a validation loop where we call predict a bunch of times on unseen data, and we take the data, compute a loss, average it over many tasks. By the way, the tasks are going to be binary classification tasks derived from C410, a whole lot of them. And that gives us a number that evolution can use for the fitness to see whether an algorithm gets to reproduce or will just go extinct. Okay. Here's an actual algorithm. This is the simplest thing you can probably imagine is linear regression. So in this case, the search would have to discover the addresses that go in each line, any constants there might be, and all the operations. And of course, the lines themselves, how many lines there should be, and so on. Let's take a little moment to consider the difficulty of the problem. Let's say you take this hand design algorithm, the linear regression, and you consider a tiny search space around it. The search space of all algorithms that can be written in these 6 lines, that can be written with only this operation. So let's use the minimal number of operations, the minimal number of memory addresses, and so on, and ask how many algorithms in this space are at least as good as that. And the answer is 1 in 10 million. Now that, well, it's a little sparse, yeah, but what tells you about the sparsity is this. Let's suppose now we consider a fine regression. So all we need, instead of doing WX, you do WX plus B. Yeah, 1 more line for prediction and also 1 more line for learning, and now it's 1 in 10 to the 12. But we're not going to be looking for stuff like this. We're going to be looking for stuff like this. Here I couldn't estimate the, we estimated the chances by just doing random search. We cannot do it anymore at this level. This actually is an evolved algorithm. It's a 2-layer neural network with gradient descent. All right? And we're going to make it even bigger. We're going to let it use any of these 60 operations. And part of it is to give it to give it less bias. We give it more operations, but also we have to be careful. We don't want to give it very advanced operations. So we drew the line at what you learned in high school, or what some of us learned in high school. So gradients were not included, and I realized a lot of people learned calculus in school, but this was a worse school, so to say. All right. So now let me tell you about how you search. So I told you how to, given an algorithm, how you know what how good it is, and now how do you find that algorithm? So we use this method, regularized evolution, which is a variant of many evolutionary methods listed there. And it's very simple. That was the appeal, very simple. Because the next simplest random search didn't work. So we have a population represented here horizontally. And at every step, the algorithm improves the population and gives you a population of children. So we start with a population of parents, you get a population of children that then become parents, and this cycle repeats over and over. In each cycle, what you do is you first kill the oldest. Can you see that? Yeah, there. And from the rest, you select the better ones according to the fitness, the reward that we just talked about. And from those best ones, you pick one at random, say the 50% best or something like that, and then you clone it. And then you mutate it. So now to tell you how these children come about, I have to tell you only what the mutation is. It's a random change. So all the improvement comes from that selection step. The mutation is a random change, can be one of these three, where you insert or remove a random line of code. And if you insert a random line of code, then it has to be a random operation at a random location with the random memory addresses and so on. Or you could randomize a bigger chunk or a smaller chunk. Yeah. That's it. That's the search process. With a bunch of optimizations, especially on how you give it data, you can get pretty fast, 10,000 per second per commodity CPU core. All right, so here's an experiment. The horizontal axis is the progress of the experiment in number of samples that you've seen so far. The vertical axis is the best accuracy found. I haven't told you how we seed the search. I told you how to go from one population to the next. The very first population is just copies of this guy. Yeah, empty code, nothing. It always outputs the same thing. The memory is initialized to 0, so it always outputs the same logic. Corresponds to the same class, which is random relative to the label. So it gets 50%. So after that, you get a hard-coded linear model. If you give it only one task, you might improve a little bit with some nonlinearity, but that's roughly where it goes, and it doesn't go much further. But if you give it many tasks, then things get interesting, because you cannot address more than one task unless you have a learning mechanism. And so indeed, it comes up with learning. Here's a slightly wrong version of stochastic gradient descent. To be fair, it doesn't discover stochastic gradient descent. It discovers gradient descent. The stochastic was forced because we're giving it one example at a time. There's nothing else it could have done. And after that, it fixes it and comes up with correct stochastic gradient descent. And in time, it discovers many of the things that the community has also discovered even recently, such as, for example, the use of ReLUs or normalizing the gradients. And this particular experiment ended here. It didn't end. We got tired. So that's what we got. Of course, it doesn't come up with the comments, although today with the LLMs, maybe it could. So we have something that came out of this. Let's now poke at it. The first thing is to notice is the scale here. It went through 1 trillion algorithms. This means that it can overfit the validation set too. Yeah. Normally, you're worried that the training process might overfit the weights because you go through many steps. Here, you should worry that the AutoML process might overfit the validation because it went through so many samples. But luckily, it does generalize. So here, we compare with another algorithm of similar complexity that also fits within our toy space. And the improvement is preserved when you go from what we use during the search to to the full-size CFR10 or to ImageNet, SVHN, MNIST, and so on. So what does it do? All right, now I'm going to be making a bunch of claims. Each of these claims was verified with knockouts and knock-in experiments, so they're not just wishful thinking. Okay. The first thing, it regularizes the inputs with a bit of random noise. Then it applies a bilinear form as its forward pass, as it were. It computes the gradients in this usual way, subtracts the label from the prediction, uses a small learning rate that it hard codes, and so on. Interestingly, normalizes them before applying them. And then it also does this weight accumulation, but in the classification case, this is like weight averaging. The scale doesn't matter. And these are indeed things that have been proposed recently in the grand scale of things. The search can even be guided. You can do this by giving it the right kind of data, or the data that you would want to solve. To verify this, we can do experiments where we repeatedly run an evolutionary search. And we do it, let's say, with a control where you have a lot of data and a case A and a case B where you give it little data and see whether you can statistically tell that some features arise in B but not in A. And indeed that happens. In this case, it comes up with noisy ReLU, which is another regularization technique. It was proposed by Nair and Hinton, and we didn't know about it, so there's no way we could have put that into the search system. We looked it up afterward when we saw it. Oh, this looks like it, and then we looked it up, and it actually had been published. Otherwise, that would have been even cooler. If you reduce the number of training steps, it comes up with learning rate decay. Again, this with overwhelming confidence, yes. And there's another example in the paper. But hopefully, by now, maybe you're convinced that this method does work. So let's get out of the toy space and do some more realistic things with it. All right, so the idea is going to be to keep using the simple primitives, to keep using the simple search method, but allow some prior ML knowledge. That's how we're going to compromise. Yeah. And in return, we're going to get realistic tasks and some state-of-the-art results. So let's say you have a puppy. And this puppy is a few weeks old. It knows how to walk, but it has never seen water. And now you take the puppy, you hold it over water, and the most amazing thing happens. It starts paddling. It's like, then the other, then the other, then the other. And it's very obvious that that's not the same movements that it does when it walks. Okay, so there's something that I've never done this experiment myself, but I saw it on YouTube, so it must be true. But regardless of whether you believe that this is hard-coded or not, no one taught you how to move the stomachs of your muscle in order to digest your food. Right? So there's clearly hard-coded behavior. And we do know that there are some aspects of walking that are hard-coded, yeah? Like pattern generators, so cells that fire regularly and their outputs are recruited informationally speaking at the time when you do have to walk or digest your food and so on. Okay, so this is work done by Stephen Kelly and the rest of us, I guess, in collaboration with MSU. That's Michigan State University for those that are not from the US. And let's take the closest thing we have to a puppy. It's this big. So we cannot really hold it over water because it's too heavy, but let's just make it walk. We want it to evolve to walk, but with a curveball. At some point in the middle of its walking, at a random time, we're going to cut the wires to one of its legs, effectively turning it into a limp double pendulum, as it were. So it's just like kind of like like that. All right. Hopefully, I mean, motivation-wise, this is what a robot needs to do, right? The dog can do it. So the robot should too. You have to adapt to things that might go wrong. And I hope the compromise is clear. Walking now is the same every time. So it could hard-code it. Evolutionary, every case, evolution has to test an individual. That individual has to walk in the same way, and it starts from the same position and so on. So that could be hard-coded. But because we're cutting the wire at a random time, the robot might be in any position. Also, we're cutting a random, we're doing this to a random leg. So this part, it cannot hard-code. It has to come up with a learning mechanism, a way of adapting. And again, we start from empty code, use simple primitives, yada, yada. So here's how some baselines do after, tuning them to death. So it's a bit awkward, you'd say, and it only works about 25% of the time because you see that, well, let's just watch it for a bit first. That's where it falls. The simulation stops when it falls. And a lot of the time it comes up with this strategy that is very hopeful. It lifts one leg in the hopes that that's the leg that will be broken, but that only works a quarter of the time. That's why it gets 25% success. So this is the evolved method. You see the leg is kind of dragging it. There, it went limp. And so it has to handle not only the fact that it has one less leg, but also the fact that this leg is a double pendulum. And if you remember your physics, double pendula are surprisingly complicated. They even have chaotic regimes as well. So, yeah. Now, it looks like it's not doing much, meaning like it looks like the motors are not doing much in response to the change, but they are. So here you can see each line is the output, is the actions that go to one of the 12 motors that this thing has. And the breakage of the leg was normalized to 500 here. So you see that a lot of motors kick in at that time, and other ones change their pattern or do nothing because they were broken. All right, so how does it work? Well, there are three variables. If you look at the code quickly, you see there are three variables that matter a lot, and the observations only come into one of them. The blue one here, S12. The other two are independent of the inputs, and they just define a decision boundary. That the position of S12 relative to the other two defines 4 quadrants. And then the decision of what code to execute is based on this. Okay? So I'm not going to explain this somewhat obtuse graph, but it tells you about what code is being executed, and what you have to see that the pattern of execution changes at the moment when the leg is broken. And moreover, that at the beginning, as you might expect, the pattern is always the same, but afterward, it has to deal with this double pendulum, so it might not be from one pattern to another, but from one pattern to something that can change, time dependent. All right, so Jeff Hinton says that you're allowed one flaky comment when you give a talk, and so this is my flaky comment, okay, this slide. If you look here at S7 and S15, so ignore the line that goes wild, that is the other one, the one that is affected by the inputs. But if you look at the other two, they're very regular periodic behavior. Yeah. It looks really like a central pattern generator. Here's I remember that you never learn how to digest food, neither does the lobster. And what you see here is 3 cells in the gut of the lobster that fire regularly no matter what's going on. and they are recruited to help digestion, to coordinate digestion. So, flaky comment. Both evolved central pattern generators. All right. Now, this, let's move to a problem now where there is less niche, where there's more competition, let's say. All right, this is work by Xiangning Chen, Chen Liang, and the rest of us. And the goal is to compromise even further and look for an optimizer for arbitrary machine learning. This is our starting point, ADAM, or rather ADAM-W, which is a correction by people here, one person here and another one not here. And it's, when people say ADAM, they typically mean ADAM-W, and well, if you don't know about it, it's a combination of momentum, the momentum optimizer, that tries to get you to go, kind of make the updates, sort of average them out to go in the same direction, so that if you have noise from your batch, or if you are maybe in a very narrow trough, then you don't end up doing too much of this, but you sort of go a little more straight. And the RMS prop optimizer, which scales the learning rate so that it goes slower when you're making big steps. When the gradients are big, you go a little slower, and so on. And ADAM combines both of those, and ADAM-W corrects something with the weight decay. Okay, so then the compromise was to, well, hopefully you see why this is important, because ADAM is the go-to optimizer probably when you have a machine learning problem, right? Occasionally, for some problems, there are niche optimizers, but in general. Right, so we want a better one. And the compromise is we're going to allow more prior knowledge. We're going to start, instead of starting from scratch, we're going to start from ADAM. And we're only going to look for the optimizer this time, not for the forward pass. So to pick your favorite model, fix that model, and now search for what would optimize that model. And the requirement, of course, is going to be very, very strict. It has to transfer well to a lot of tasks. So in other words, we're looking for a train function that receives weights, gradients, and some state vectors, which in ADAM are the momentum and also the aggregated momentum, the aggregated squares of the momentum. But here they're arbitrary. And then returns the update together with the state so that it can be reused in the next step. And then you get the fitness in the usual way. You train your model with it and see how good the model is, and that's how good the evolved code was. Okay? So far, so good? All right. So here, this is a difficult problem too, even though we've made all these simplifications. What you're seeing here is the training, the evolution, sorry, of two different search experiments. And the horizontal axis is the same as before, the progress in the experiment. The vertical axis is how well the best model at that point does on unseen data. Yeah. And most of the cases go like the blue line, even though it optimizes what you gave it, that doesn't generalize. But occasionally it goes like the orange line, and if you pick the best of the experiments ever run, and you get this. Two things to notice about this, that it's now called the Lion optimizer. The O stands for evolved. I told them that it should be Eve because, it was Adam, and now you have an evolved algorithm. It should be Eve, but no, they said, no, it should be Lion. Okay. A cool thing about it is that there is only one state vector passed through. Yeah. This means that if you're training an enormous model, you have much less requirement on your memory. Yeah. The other weird thing is this sign operation that seems to just willy-nilly get rid of information on the update. All right, we'll come back to what's going on here. But first, I think people are more motivated to listen to an explanation when they've seen that the thing works. So on the left, you see ImageNet trained from scratch. And now the pattern in this many verifications of the algorithm that I will show you next is that we're going to compare Lion to Atom. And the reason for doing that is that Atom is good in many applications, right? And so we want to show that this is equal or better in many applications. So here's ImageNet trained from scratch on the left, and on the right, it's a fine-tuning of ImageNet. And in both cases, you see better accuracies. And if you're not interested in going all the way to the very end, you can get huge speed-ups. In all cases, you have the memory saving. Right now, we're talking just making sure that with that memory saving, it works. All right, I have half a slide on LLMs, so I fit in the and this is for fine-tuning the LLMs, not for training them. You can guess why. And yes, it works, not all the time, but a lot of the time, and it doesn't fail catastrophically. On the right is the training of a diffusion model, where you see the similar resource savings and even better loss in the end. And for vision language contrastive learning, it also does well. It does very well. Here, we use data factor because data factor was the one that had been used in the baseline. But this is state of the art. If you go look at ImageNet and I think they labeled it, in that website where they keep track of it, they labeled it as basic L. Basic is the model, and the L stands for trained with Lion because the previous one would not have been state of the art today. So, hopefully that convinces you that, yeah, it works. So how does it work? Well, there was a pattern in what I was saying that fine-tuning, right? And when we trained from scratch, was in data sets that were not enormous. So maybe there is some regularization going on here. And indeed, remember that we were getting rid of some information in the update. So that agrees. And, well, the way to look at this is let's look at the training. And the training loss is indeed bigger so it's worse. Lion is worse in the training loss, but better in the validation loss. And now one test you can do is see where this whole thing lands at the end of training one particular model, see where it lands in parameter space, and look at the shape of the loss with respect to the parameters, and displace it a little bit, and see how much worse the model gets. In other words, you're looking at the curvature of the loss with respect to the parameters. And what you see is that when you train it with the Lion optimizer, it's flatter. So it's less sensitive to perturbations of those parameters. And maybe, therefore, in perturbations of the activations that you're going to multiply those parameters with. OK, so I hope this convinces you that it kind of works. In summary, we evolve at different levels of prior knowledge, in increasing levels of prior knowledge and practicality. And in all these cases, we get machine learning algorithms from simple primitives. Notice that in all of the cases, we're evolving at the code level. We started with the zero approach, which was in a toy setting. And we gave it almost no prior knowledge. And then we went to the one where we allowed it to hard code some things, but it was still very limited in its prior knowledge otherwise, and it can evolve the situation for a realistic robot. And in the end, we compromised much more by letting it know about a state-of-the-art model and starting the search with a state-of-the-art optimizer and improving it. This is work done by a lot of people listed here. Thank you for listening. No questions, bye. I think there was one there.
Hello?
What's the fun in it otherwise?
Yeah, exactly. Okay, that's a great talk. Thank you very much. I don't know if I missed it, but did you mention like some estimates how long it takes to evolve these things and with like CPU hours?
Yeah.
Did I miss it?
So in the first experiments were the ones where we could, because the tasks were smaller, we could avoid the most sample complexity. And there it was about 1 trillion samples. So in terms of physical time, a few days, like 5 days or something like that, on 10,000 commodity CPU cores.
Okay.
That was for the big experiment, you know, the one where there was the big curve.
Largest, how much was
it? The other ones where we did many experiments, we didn't do that. We went to smaller setups.
Okay. And if I may, like a second question is, so you showed a lot of techniques that were not recently published in machine learning that you rediscovered de novo, but did you discover a novel technique in machine learning that, you know, like this?
Right, yeah, that's a great point. So for the first half of the talk, no, and for the second half of the talk, yes. Right. I guess that's what I was trying to address with the the Lion optimizer, for example, would be a novel technique. But maybe you are asking specifically about the case where we gave it no prior knowledge, and in that case, no. That as far as we know, no. Right. It's always a difficult challenge in that you're looking at this code, yeah, and you're trying to see, well, what does it do? And you're obviously much more likely to recognize or to know what it does when it's something that you have seen before. So it's like, oh yeah, that's weighted averaging, and yeah, that's a ReLU, and yeah, maybe there is something novel there, but you can't quite see it. Of course, the way it combines things, it's always novel, right? That's like kind of like when you're doing architecture search, right? You find something new, but yeah, a very interesting thing would be to see if we can get that kind of setup with no prior knowledge to do things maybe more differently. For example, there is some bias that you might have. I say very little prior knowledge, but it's not zero really, in spite of the title. So, for example, having matrix multiplication, right? That means that coming up with a forward pass is not, the forward pass of a standard neural network is fully connected, is not that hard, right? All you have to do is multiply by something, then add something. The learning is harder, so that was the interesting part. But maybe if we could go to even more basic things, right? Like don't know about matrices. But of course, we would need that much more compute. I'm not sure we are ready.
Yes.
So that was a long answer, sorry.
That was great, thank you.
It's 2 questions.
Just direct follow-up to the training cost. You showed that slide where you said optimizations, you did 10,000 algorithms evaluated per second per CPU core.
Yes.
Pretty early. So a couple of questions about that. And during the talk, I did the math because I was like, well, can we also do this? And I got to, 10,000, so that's 10 to the 4 seconds per day. It's roughly 10 to the 5. So that should actually only be 1,000 CPU core days. That is something. 100 CPUs for 10 days. Actually, CPU cores. That's something a lot of us could do.
Sorry.
But then your answer was now 10,000 for a couple of days, and that didn't match up for me. Why?
Yeah, but I am absolutely sure of the final number because I suffered through it. So I am not going to do math in front of a room in my head, but trust me, it is more like the other number.
Right, so about 10,000 for a couple of days.
Yeah, however, I don't think you need to do the whole search to get interesting stuff. So, for example, remember the bit. Well, remember the bit where there were ablation experiments comparing what happens if you have more data or less data. That was an order of magnitude less compute because I think we seeded it with a neural network for the forward pass. So that we could get something that we would immediately understand. And so what training it came up for it or something like that. And now you reduce the cost a lot, right? Mm-hmm. Yeah.
When reading the original paper, I thought, well, a lot of it must have gone into that engineering 10,000 function evaluations on a CPU core in a second. How do you do that?
Yeah, well, the first
it
thing...
sounded crazy to me when I read it.
I know, right? Yeah. First of all, we coded it in C++. Yeah, we started with Python, and then we got a jump of 3,000x when we went to C++. And we optimized even little things like how much for example, the dispatch cost, right? When you see, I have to. This was an interpreted language, yeah. Mm-hmm. So when I see an instruction, I have to go there. You try to reduce the number of redirections, use templates as much as possible. What else? But the data was very important. So for the data, I said very briefly, CFAR10 derived binary classification task. So the binary classification task is obvious, right? You take two classes and you just restrict your set to those, and so then you get 10 times 9 divided by 2, some, whatever that turns out to be, which I'll get into another argument if I say it. But in addition to that, and probably more important, or as important, was, obviously that reduces the size of networks that you need in addition to having less data. But we projected the features to a space that I think was about order of 100 dimensions. So instead of having whatever CFAR10 is, I think 32 times 32 times 3, which I'm also not going to work out, we reduced it to about 100 by doing random projections. Yeah, and that helped a lot.
And that highly engineered code, is that code that can only run on a Google cluster, or is that
no? That commodity CPU. By commodity CPU, I mean the run-of-the-mill cheap CPU. Mm-hmm. Yeah.
And is that available? Or?
I'm sorry?
Is that code available, or I forget?
Yeah, it's open sourced.
That's cool. So it's actually, we could download this, run this on our machine, should work.
Yeah.
Of course, with some help, but cool. That's awesome. Who was first? People there. Where?
There was also one up there for a while.
All right.
Almost.
Hi, thanks. So I was just thinking, with the linear regression example, what's like the first thing it kind of stumbles upon to get anywhere above 50% accuracy? Because like it just feels at that point it's just like shuffling through stuff until something gives it like any signal. And do you know what that was?
Yeah, it's kind of like the punctuated equilibrium, right? Like bomb.
Yeah.
The first step is, empty code, really, the first step is just connecting the input to the output, right? And if you connect the input to the output through that one vector multiplication, that gives you the hard-coded. It finds it super easy once you have that. No, I take that back. Keep in mind that this log was also log in the horizontal axis. So even though it looks like a lot of stuff is happening at the end, you're waiting a really long time at the end for those things. Maybe if I can go there. The orange labels here tell you a bit about what was just found. So we went and looked at the model there, and what was in that model that wasn't before, that we could understand, and that comes back to the other question about, could there have been something new here? There could have been. So for example, here it was the ReLU and so on. Is that what you were getting at? Maybe that isn't.
Yeah, that is. Thanks.
Oh, okay.
Yeah. There, I think.
Well, we're gonna have a prize for the best thrower.
Okay, this is the right way. Okay, cool. Yeah.
We broke it.
Yeah, probably. But I tried to shout anyway. So very impressive work, I think, also in terms of various tasks that were tested here, and where you show that Lion has an advantage. One point I was curious about is that you usually, whatever task you take, you usually have a look at ImageNet classification task, either zero shot or full fine-tuning. What we saw in experiments with language vision OpenClip is that situation is interestingly different for another task types like retrieval. Have you tried to have a look at different task type apart from ImageNet classification in the cases we are playing with vision or vision language?
Okay, so there's a lot of ImageNet there. Was that it, or were you still talking?
No.
Okay. Just
so have you tried to have a look at retrieval, for instance, at language vision as a task type?
So the answer is no,
okay.
Except for the ones that I showed, like, for example, the LLMs and diffusion, which is not a classification task.
It was more related now to ImageNet stuff. So
for images, whether we did just classification, well, we also did the generation.
Okay, so language vision clip, right? Quite impressive result with basic on ImageNet classification,
yeah.
Zero shot, whatsoever.
Okay.
Have you had a look at retrieval there? No.
No, I don't think so. I don't think so. And I think I want to say...
Yeah, that would be a low-hanging fruit. You can use clip benchmarks to immediately evaluate whatever you did on retrieval and just have another strong point. Probably it will be better.
I think there is considerable effort in going to each scenario, setting it up, tuning the parameters and so on. So I just want to say a word in favor of Shengmin and Chen here, that they put a lot of effort into trying things, and I think they were very open about sharing where it didn't work, but where it didn't improve upon the baseline, where they gave the same results. If you look in the paper, there is more. I don't know about specifically the one that you mentioned.
Yeah,
but
sure. That's why I was
more.
kind of complimenting on the variety of tasks that were tested.
Thanks,
and was surprised that an easy, low-hanging fruit, the retrieval, was not evaluated. You don't need to tune anything. You just take the model that you have anyway trained on language vision, so clip-like, and then you evaluate it also for retrieval. You immediately get your numbers, and you can report them.
I'll pass the word.
Yeah, thank you. And in terms of reproducibility, of course, it would be great to use less and less stuff that is trained on completely private closed-door data, because as a community, we cannot even check the results then. So using whatever open data sets to do these experiments would allow to check up by independent groups. So
yes, I think they try to, strike a balance, right? You take the LLM and you fine-tune the LLM, but you also train on ImageNet, for example. Yeah,
thanks.
That's first. Because it's undeniable that LLMs is where it's at now, right? And it's very hard to get away with not using data that is not maybe fully available.
Well, I think that's not really true, right? So you have a lot of open data sets by now: Red Pajama, Pile, Falcon-based stuff. big science offspring, so a lot. Like
I think, yeah, I see your point. There are other constraints that we can talk maybe in private later.
Okay.
When you're working in a company and you have, let's talk about it later.
Okay, cool, thanks.
Yeah.
Hi, so this is a question from the online audience. So the question from Yihang Shen is, you mentioned that you use evolutionary strategy. Is there a reason that you decide to use a simple strategy, which is by the way great, instead of more sophisticated strategies such as RL?
Actually, it wasn't an evolutionary strategy. We're doing, for the most part, symbolic search. So the optimization is discrete. There is a continuous component, of course, when you have to, in the code, there might be a constant, and that constant has to be optimized continuously. But we wanted one algorithm for everything. So we used linear genetic programming for that. That was just a clarification. But it wasn't the spirit of the question. The spirit of the question is, why didn't we use RL? In here is, we wanted to keep things as simple as possible. Also, in the previous work, we compared the performance of RL and I say this with a pinch of salt because we didn't try it in this search space, but I realize that this is a question I'm going to get for every search space, and I cannot do it for every search space. But in a previous case, we compared RL with regularized evolution as well pretty thoroughly on a scenario that was designed for RL. The paper has the title regularized evolution ... And there you can see probably the basis of our choice.
Can I do another one? So there's another online question from Gabriella. It's, do you think your approach could be used to discover the successor to the transformer architecture?
Yes. No, I don't want to. I don't want to trivialize the question, right? I think it's a great question, and obviously I don't know. Yeah.
Esteban, great talk again. You looked a lot at evolving the architecture, the genotype, basically over generations. Did you also consider learning or adapting at least within a lifetime, where you would not throw the weights away, but you would adapt in a more continual way?
Let me try to understand the question better. And in the case of the robot. Mm-hmm. Right? That is an algorithm that has to sort of change itself. There is, during the lifetime, so it's zero shot, that case. Is that the sort of thing you're talking about, or did I misinterpret?
You would kind of also grow the network or change the architecture?
No, I see. Okay. No, we did not try that. Okay. Yeah. Sounds tricky.
Yeah, I mean, our brains do adapt during our lifetime. They change a lot over our lifetimes, so something does happen there. Yeah. Yes. I think you need to constrain what kind of changes you allow to happen.
Yeah, mostly by reducing.
Yeah.
Something worth trying, but we haven't done it yet.
Thank you.
Thank you. So a common criticism I've seen of a lot of neural architecture search work is that the discovered architecture is only able to make an incremental improvement over the baseline, which seems to largely be a function of the design of the search space. So in a sense, the sort of much more open-ended search spaces that you explore in this work seems to be kind of crucial for being able to make sort of leaps in design. But kind of along the lines of the online question, I wanted to ask, if our goal is to have an automated method that is going to, make the next big breakthrough in deep learning mechanics, the new transformer or whatever, to you, is that more a problem of finding the precise amount of priors to build into the search space, or is it more a question of finding the correct problem to point the algorithm at?
Yeah. The way I presented it here, obviously it sounds like it's about the right amount of prior knowledge, right? But in searching for example, the problem about the robot, right? You could have imagined instead doing something like, okay, these robots are usually trained with something like CMAES or some form of RL, like PPO or something like that. Okay, so then that's what we should go at, right? We should try to improve the PPO or the CMAES and so on. But that means that then you get this very slow training in the middle of the evolution loop, right? And so that's a bad choice of problem. The adaptation problem instead means that it gets to do what it would have done within the loop in evolutionary time now, because it can hard code things. And the thing that it has to, the learning algorithmic part that it has to come up with, that one gets evaluated during one episode. So it's quick. So it's kind of ideal for this kind of search. Right, very quick. So there is even though I didn't highlight it, there is a big component of choosing the right problem. I think in the last result, the one about the optimizer, there it was more like, oh, that's I think Xiangning and Chen were like, this is what we really want to do, so let's just push through. And that one wasn't driven by convenience, let's say. So I think that answers part of your question, but maybe not all of it. Can you tell me what I'm forgetting?
Yeah, I think the idea was sort of weighing these two components of having the right sort of prior information, but still an open-ended search space versus choosing the right problem. Like, which to you is the sort of more crucial component of being able to come up with an automated method that can make real sort of breakthrough leaps in design.
Right. Yeah, I would put the weight on choosing the right problem, because if you look at the last, for example, result, there the change is pretty small, right? If you look at I don't know, by whatever metric, like the number of lines that change or what, it just puts this sign operation there and it removes a few other lines. It's kind of along the lines of what was being done before. And yes, it works better, but we haven't discovered a completely different kind of unknown machine learning. I think that if you give it that much amount of prior, you're going to get the prefabricated house. So I would put my my money on the picking the right problems. But of course, until we actually find that, this is just a guess.
The poster session is starting now. Maybe one quick question, one more question. Yeah. Go ahead.
Yeah, thanks for the talk. I have one quick question to the AutoMLZero, where you discover the SGD and then discover later on the nonlinear ReLU activation function. So I guess that like the gradients that you compute, which is just like the outer product, with the ReLU, the backward pass would change. Was it then immediately after the ReLU also discovered that the backward pass, so to say, or the gradient computation has to change? Or why is there, because like it's only with the ReLU an improvement, but I would assume that with ReLU maybe it decreases the performance because the backward pass is just incorrect then.
Mm-hmm. Yes. Let me go to that plot. What you see here, there's a lot of stuff that happens in between. So these experiments are going through 1 trillion models, so we cannot save them all, because then saving them would be the rate determining step. So we have to lose a lot of information and only record snapshots.
Yeah.
So when I say here the ReLU appeared, it means that the ReLU is here. The ReLU was not in the previous snapshot. The previous snapshot had much less accuracy than this one, but there were other changes as well. And of course, I don't remember now the code of that particular algorithm in that population, in that snapshot and in the previous snapshots, but it's very likely that there are other things that happened as well, and that one was the most notable to us.
All right, okay, makes sense. And it's also interesting that the ReLU is then in the best algorithm again. It's just like a linear transformation, no non-linearity anymore in it, right?
What do you mean by no non-linearity?
So it's just like dot products to compute the predict in the predict function, right?
No, with the ReLU, there's dot products followed by a ReLU. The ReLU itself is the non-linearity, right?
Exactly, no, but in the best evolved algorithm.
Oh, in the best evolved algorithm. Well,
That's interesting.
the bilinear interaction is non-linear, right? I mean, it's because it's the inputs times the matrix times the inputs. Is that a reasonable thing to say? X times A times X is like x squared.
Yeah, okay, yeah, makes sense.
Yeah, it's not obvious when you're looking at the code, right? But yeah.
Okay, thanks a lot.
I hope I'm saying that right. Anyway, we can look at it later. It's been 3 years, I'm sorry.
All right.
Thank you.
Thank you very much.